Hello. Today we'll discuss context-free grammar. So, context-free grammar, formally we can define by using this. So, a definition: a context-free grammar or CFG or context-free grammar is defined as four tuples. Vn means non-terminal, sigma is terminal, P production rule, and S is the start symbol. Where P is a set of production rules. And the form of the production rule is of that A to alpha, where this A belongs to Vn means non-terminal and alpha belongs to Vn union sigma its star combination. So on the left hand side of the production is free from any context. That means there is neither left context and there is or nor the right context. So the production of this form of grammar is basically called the context free grammar, and this context free grammar are basically used in the design and implementation of the compiler. So the designer of compiler often use such kind of grammars to implement component of a compiler like parser, like the parser and scanners, code generation or code generator, etc. So now we'll give an example. Suppose question is, show that the grammar described by the following grammar rule is a context free grammar. So the production of this question is S or this S, this S, this or so obviously if we basically the question is so that the grammar described by the following grammar rule is a context free grammar. Now from here, what is non-terminal? What are the non-terminal symbols? Obviously it is only S. And what are the terminal symbols here? It is plus, minus, multiplication, division, bracket, and A. These are basically non-terminal symbols. Since we have seen from these production rules that all the given productions are of the form A to alpha. That is, in the left hand side there is a single variable or only one variable, so which does not have any left or the right context. Hence, it is a context free grammar, right? Hence, it is a context free grammar. Okay. Now, context free. What is context free language? So, context free language. What is context free language? So, the language generated by context free grammar or CFG are called context free language. Now we define derivation. What is this? So derivation can be defined as the process to generate string of terminals by replacing non-terminals in the right hand side of a production. So formal definition: a derivation can be defined as the process to generate strings of terminals by replacing the non-terminals in the right hand side, of a production. So this is basically the derivation. Now we'll define uh, parse tree. Parse tree. What is parse tree? So as we know that a string generated by the context free grammar can be represented by a hierarchical structure. We call it as a tree. And hierarchical structure is that structure in which elements have some relationship with each other. Yeah. For example, suppose a node A is a parent node of B. Then A can be accessed through B and vice versa. Now we define the parse tree. So a parse tree also sometimes we call the derivation tree. Sometimes we call the syntax tree. Sometimes we call the production tree. Etc. So a parse tree for a context free grammar, suppose G, has some characteristics, has the following characteristics. So number one characteristic, every vertex of a parse tree has a label. So every vertex of a parse tree has a label, which is either a variable that is non-terminal or a terminal or a terminal from null or sigma union epsilon, or sometimes we call this null. Okay. Second characteristics, the root of a parse tree, the root of a parse tree has label S, and this S is basically the start symbol. And number 3, the level of an internal vertex. The level of an internal vertex is always a variable, or non-terminal. Now, fourth characteristic, if a vertex has, suppose the vertex is A and has k children, with labels, suppose A1, A2, A3, AK, then there exists a production of the form A2, A1, A2, A3, A of K in the context-free grammar in CFG. Now, these are the some characteristics of a parse tree. Now we'll give example. So, example. Suppose let G is a grammar, or G1 is a grammar where S or A is non-terminal, A, B is the terminal, and P is the production, S is the start symbol. Where P or the production rules are given S to AA, A to AAA, or BA, or AB, or A. Then the derivation tree for the string, then the parse tree for string B, B, A, 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 B will be, what will be the parse tree for this string? Now, we have to generate this string by using these production rules. Now, if we starts from this, this is the derivation of AA, we have starts from here. Now, as the string, first symbol is small b, that means we can replace this A by B of A, and then again A. Then we can replace this A by B, B, A, and A. Now, as the string is B, B, then A. So now this A can be replaced by B, B, and then A. Now this A on the right hand side, this A can be replaced by triple capital and triple variables, triple A. Now we replace this A by small a, and again now this B, B, A, and this A will be replaced by again A. this A, okay, and now A will remains. Now this A will be replaced by AB. So B, B, A, and this A can be replaced by using this A, B. So we can replace this A, B. Now this A can be replaced by small a, B, B, A, and B. So now we have generated this terminal string from this production rule, that is B, B, then A, and B. So what will be the derivation tree? So we have to start from here. As we know, the S is the start symbol. So S from S. So now this is S from A. First this A. Okay, because this is a production rule. Now this A has been replaced by B and A, and it will remain same. Now this A will be again replaced by B, A, and then A is replaced by A. Now this A will be replaced by triple A, as we have seen here, this A. Okay, so now this A has been replaced by small a, this also is small a, and now this B will be replaced by A, B, and now this A will be again replaced by A. So this is the derivation tree or the parse tree for the string B, B, then for A, and this B. Now we'll define what is yield of the derivation tree. Right? So what is yield of the derivation tree? Yield of a derivation tree or the parse tree Okay. Now, what is the yield? We define like this: the yield of a parse tree or derivation tree is the concatenation of the labels of leaf nodes in left to right ordering without repetition. Without repetition. Okay. So this is the definition of the yield of a derivation tree. Now I'll give an example. Suppose we have a derivation tree like this. Okay. Now what will be the yield? Yield means concatenation of the labels of the leaf nodes. So these are basically the leaf nodes. B, and A is a leaf node, right? We have to concatenate of the leaf nodes in left to right ordering. This from left to right ordering. This is left to right ordering without repetition. So the yield of this derivation tree will be, yield is obviously B, A. So this is basically the yield of a derivation tree. Now we'll give another definition, which is a leftmost derivation and the rightmost derivation. So leftmost derivation or leftmost derivation or it will be together, leftmost derivation. So what is leftmost derivation? We can define a derivation A 2w by any number of substitution is called leftmost derivation if we apply production rules, if we apply production only to the leftmost variable every time, at every step, or every time, at every step, then we call it as a leftmost derivation. Similarly, what is rightmost derivation? Rightmost derivation, same. So a derivation, again we define a derivation a to string by any number of substitution is a rightmost derivation if we apply production only to the right most variable at every step. It is leftmost variable, and here it is a rightmost variable at every step. So we have defined what is leftmost derivation and the rightmost derivation. Now we'll give an example. Suppose we are given the production rules of this form h to h, this, and h multiplication this, and bracket of s and a. These are the production rules of a context-free grammar. Clear? It is a context-free grammar production rule. Now, if we want to find leftmost derivation, suppose we have to generate a string of the form a, this, a. We have to generate this string. Okay. And to generate this string, what will be the leftmost derivation and what will be the rightmost derivation? So now we start from here, s derive s to s minus s. Now we can replace, in case of leftmost derivation, we have to replace leftmost variable at every step. So this is the leftmost variable s. So we can replace these variables every time, every step. So we can replace this s to s, because this by using this production. Now this is of the form. Now we can replace this s, this is. So it will be a, this, and this. Now this s can be replaced by this a, because every time we have to replace the leftmost variable s, and finally a of a. So this is the leftmost derivation. Now similarly, what is the rightmost derivation? We again start from here. We can write s, this. Now we have to replace every time step the rightmost variable. So it will be this s a. Now this variable can be replaced by s a, and now this variable s a, and now this variable a. So these are the two different derivation. One is the leftmost derivation and the rightmost derivation for the string a multiplication of a minus subtraction of a. Yeah. Now, so this is one of the example of this leftmost as well as the rightmost derivation. Now we'll discuss the ambiguity in the context-free grammar. So ambiguity in CFG or the context free grammar. Now, what is the meaning of this ambiguity in terms of the context free grammar? So first we will give a formal definition, then we will discuss it. So definition: a context free grammar G is said to be ambiguous. Ambiguous if there exist at least one string, and that string should belongs to the language generated by this grammar, having two or more distinct derivation tree. That is, the meaning is that two or more leftmost or two or more distinct leftmost derivation or two or more distinct rightmost derivation. So if this criteria fulfill, then we say that the context free grammar G is a ambiguous, or there is an ambiguity or contains in the context free grammar. So we have to check for a particular string, any string which belongs to this grammar, and we have to find for this string two or more distinct leftmost derivation or two or more distinct rightmost derivation. Now we'll give an example. Suppose the question is show that the language of all non-null string of is defined by CFG or context free grammar G is equal to S A S to AS or SA or A, S is ambiguous. Now, what will be the solution? Solution is we have to find any string that belongs to this that is basically generated by this grammar. So obviously from these production rules, it is clear that a string will be generated. How? From S to S or from S to A, then AS or AAA. So we consider this string triple A. Clear? Now we try to find, is there exist two or more distinct leftmost derivation or two or more distinct rightmost derivations, right? So starts from here. So now S to S and this is, if we so this is, we can replace by this s by sa, or we can replace this s by a. Now in this case, this s is you can consider that s is a rightmost variables or the leftmost variable, because no other variables are exist in this production rules. So that's why we replace by this using this. Now we can generate the same string by using this concept, right? That sa we can replace by this. Now we can replace this s by sa or as. Now this is can be replaced by a. Clear? If we consider that all are basically the leftmost derivations, okay, we have to find. So all are basically, we consider the leftmost derivations. Now obviously we have seen that the first leftmost derivation and the second leftmost derivation, these are two different. Again we can find another derivation like this s2, suppose as, and this s can be replaced by as, and this s can be replaced by a, and so on. So now for the same string triple a, we have obtained three different derivations of leftmost derivation, three different or three distinct leftmost derivations. Now if we draw the parse tree, then it will be more clear. So starts from s, this will be s. Now this s will be replaced by sa, and this s will be replaced by a. Clear? So a, and from here we can write this. Now this s can be replaced by as, and this s can be replaced by a. Clear? So obviously from this parse tree it is clear that they are different. The parse tree are different. Obviously from here also s to a, s, then a, s, and then a. Hence, as we have clearly mentioned in the definition, that if we find for a particular string, at least one string, two or more distinct leftmost derivation or two or more distinct rightmost derivation. So here we have obtained three distinct leftmost derivation, or are leftmost derivation. So we have obtained three distinct leftmost derivations. So obviously the grammar G is ambiguous. So hence the grammar G is ambiguous. G is ambiguous. Okay. Now, why do we care about this ambiguity? Why do we care about ambiguity? Why? So now, for this reason, to explain this, again we consider a grammar of this form. Obviously, we have given the example of this, and now we'll again we consider another grammar. Suppose the grammar production rules are, suppose the grammar G with production rules are given in that form. Suppose E to E plus E, E to multiplication of E, bracket of E or A. These are the production rules. Now we consider a string, let the string is A plus A into A. Clear? Now first we'll check whether it is ambiguous or not. Now we'll generate or we try to generate two or more distinct leftmost derivations. Okay, so first leftmost derivation, So we'll start from here. E derived E or plus E, then leftmost derivation. So this variable will be replaced every step. So this E can be replaced by A, then this. Now this variable will be replaced. So A or this E can be replaced by E multiplication of E. Now it will be A. This variable will be replaced. Then A or A multiplication of A. Now second leftmost derivation will start from E to A multiplication of E. Now we'll replace left variables. So this can be replaced by E or E in multiplication of E. Now this variable will be replaced by, so it will be A plus E into E. Then this variable will be replaced A of E. Now this variable E will be replaced. So what we have seen? So we have obtained for the string A plus A into multiplication of A, there is a two distinct leftmost derivation. Now if we draw this parse tree for these two leftmost derivations, it will be look like this. So E to E, then plus, then E. So go this from this first production rules. Okay. Now from the for the leftmost variables, that will be replaced by A. So in this diagram also it will be replaced by A, or in the parse tree it will be A. Now this variable will be replaced. So it will be replaced by E, then multiplication, then E. Now leftmost variables, that will be replaced by A. Now this variable, it will be replaced by A. And for the second leftmost derivation, so the parse tree will be this E, this and this. Now the leftmost variable is E, so it will be replaced by E plus E. Now this leftmost variable, it will be replaced by A. Then this will be the leftmost variable A, and this will be the leftmost variable A. Okay. Now if we consider, suppose the value of A is 2. Okay, let the value of A is equal to 2. Now if we put this value for if here A 2, the value of A is 2. If we put this 2 leaf node 2, here also it is 2 and 2. Now we proceed bottom up approach. So now first it will perform this 2 multiplied by 2. So the value of this node will be 4, and here it is a 2. Then 2 plus 4, it is a 6. So the result will be 6 in this case. But in this case, first it will perform the addition. So 2 plus 2, it is 4, and here it is a 2. 4 multiplied by 2, it will be 8. Right? Now what actually happened? We have seen that, but the correct answer will be 6. But what we have seen, if we find a context-free grammar and it has for a particular string, if we find 2 or more distinct leftmost derivation or 2 or more more distinct rightmost derivation, then the grammar is ambiguous. And if there is an ambiguity in the grammar, that means the outcome will be different. So that's why we have to care about this ambiguity. Okay. So thank you.